Solid rocket boosters are the original muscle of spaceflight. Simple, reliable, and about as subtle as a fireworks show at a library. Their design is straightforward. A solid mixture of fuel and oxidizer is packed into a tube, and when ignited, it burns from the inside out, producing a massive stream of hot gases that shoot out the back and propel the rocket forward. Once lit, there's no stopping, no throttling, no shutdown, just a one-way ticket to orbit or a very expensive campfire. That's why they're often used as the first stage of launch vehicles, giving that initial kick to get heavy payloads off the ground. Think of them as the muscle-bound bouncer at the club of space. Loud, strong, and not exactly subtle. Their simplicity is their greatest strength. With fewer moving parts, there are fewer things that can go wrong, making them incredibly reliable for missions where brute force is needed. The Space Shuttle's twin solid rocket boosters are a classic example, providing the majority of the thrust needed for liftoff. Modern rockets like the Ariane 5 and some commercial launchers also use solid boosters for their initial ascent. But there's a catch. Once ignited, you're committed. If something goes wrong, there's no way to stop the burn, and the entire mission could be lost. That's why solid rockets are best suited for missions where you need a powerful, short burst of thrust, like getting off Earth or launching ballistic missiles. Their ruggedness makes them ideal for military applications, but their lack of control means they're rarely used for delicate orbital maneuvers. But what happens when you want more control than a one-way ticket to orbit? Liquid-fueled rockets are the refined, professional drink of the spaceflight world. Smooth, controllable, and capable of refilling and restarting mid-flight if necessary. Their design involves storing propellants, typically liquid oxygen and a fuel like kerosene or liquid hydrogen, in separate tanks. These propellants are pumped into a combustion chamber where they are mixed and ignited. Thanks to sophisticated valves and turbopumps, engineers can precisely control the flow rate, ramping up the power for launch, throttling down for delicate maneuvers, or shutting down entirely to perform mid-course corrections or landings. What makes liquid rockets so special? They offer unmatched flexibility and precision. Missions that involve complex maneuvers, docking with space stations, or landing on planetary bodies rely on the ability to regulate thrust dynamically. Think of them as the manual transmission of rockets, a little more complicated to operate but far more adaptable. Their development dates back to the early 20th century, with pioneers like Robert Goddard pushing the boundaries of what could be done with liquid propellants. Modern heavy-lift rockets, such as the Falcon 9 and SpaceX's Starship, employ advanced liquid propulsion systems, making them the backbone of today's space exploration efforts. However, all this complexity adds a lot of plumbing, thousands of feet of piping, valves, and pumps that need to stay in perfect working order. Failures can be catastrophic, but when everything goes right, the power they unleash is nearly unmatched. Their ability to restart and throttle makes them perfect for reusable rockets, but the engineering challenges are immense. But what if you want to go even further, at even higher efficiencies? Would you dare to push beyond chemical rockets? Hybrid rockets are the wild card of the rocket world, part solid, part liquid, and a little bit unpredictable. They use a solid fuel, like rubber or plastic, and a liquid or gaseous oxidizer, like nitrous oxide. The fuel and oxidizer are stored separately, which makes hybrids safer than their solid or liquid cousins. When you want to fire up, you just inject the oxidizer into the combustion chamber, and the magic happens. Hybrids are easier to control than solid rockets and simpler than liquid ones, making them a favorite for experimental and amateur rocketeers. They're like the indie band of the rocket family, quirky, creative, and not afraid to try something new. Their main advantage is safety and control. Because the fuel and oxidizer are kept apart until ignition, the risk of accidental explosion is much lower. Plus, you can throttle the engine, shut it down, and even restart it, something solid rockets can't do. Virgin Galactic's Spaceship Two is a prime example, using a hybrid engine for its suborbital flights. Hybrids are also popular in educational and research settings, where safety and simplicity are key, but they're not without their drawbacks. They're generally less powerful than liquid or solid rockets, making them less suitable for heavy lifting or deep space missions. Still, their flexibility and safety make them a promising option for future space tourism and experimental launches. Their ability to be throttled and shut down mid-flight makes them tempting for future deep space missions. But can they truly rival the heavy hitters in lifting capability? Or will they remain the spaceflight equivalent of almost? Ion thrusters are where things get sci-fi. Instead of burning fuel, they use electricity to accelerate ions, charged atoms, out the back of the rocket at incredible speeds. This creates a tiny but constant push, perfect for long-duration missions where efficiency matters more than raw power. Ion thrusters are the marathon runners of space travel, slowly but surely building up speed over months or even years. They're used on probes like NASA's Dawn and Deep Space One, where every ounce of fuel counts. But don't expect fireworks. Ion thrusters are so gentle, you'd need a microscope to see the exhaust. They're the quiet, mysterious type, the kind that sneaks up on you and wins the race by outlasting everyone else. Their efficiency is unmatched. Because they use so little fuel, spacecraft can travel much farther and for much longer than with chemical rockets. They're ideal for missions to the asteroid belt, deep space probes, or cargo ships heading toward Mars. But they're not for everyone. Ion thrusters produce very little thrust, so they're useless for launching from Earth or making quick maneuvers. They're best suited for missions where patience is a virtue and slow, steady acceleration is the goal. Their ability to run for thousands of hours on a single tank of propellant makes them perfect for long-term exploration. But their gentle push means they're not for the impatient. But what if you want to go even faster, even farther, and maybe even break the laws of physics? Nuclear thermal rockets are the stuff of science fiction made real. They use a nuclear reactor to heat a propellant, usually hydrogen, until it's screaming hot, then blast it out the back for thrust. The result? Way more power and efficiency than chemical rockets, with the potential to cut travel time to Mars in half. These rockets are still mostly experimental, but they could be the key to deep space exploration. Of course, there's the small matter of radiation and the fact that you're strapping a nuclear reactor to a rocket. But hey, when you're trying to reach the stars, sometimes you have to play with fire, or in this case, a reactor. The potential is enormous. Nuclear thermal rockets could revolutionize space travel by making interplanetary missions faster and more efficient. But the challenges are just as big. Handling nuclear materials safely in space, preventing proliferation, and avoiding catastrophic accidents are serious hurdles. Still, with ongoing research and the growing international interest in lunar and Martian bases, nuclear thermal propulsion may become the backbone of interplanetary travel. Their ability to deliver high thrust with minimal fuel makes them ideal for crewed missions to distant planets, but until we figure out how to make and store antimatter safely, it's mostly a dream. So what's the next step in the evolution of rocket ships? Solar sails are the ultimate in minimalist rocketry. Instead of fuel, they use the pressure of sunlight to push a spacecraft forward. Imagine a giant, ultra-thin sail catching the solar wind, slowly but steadily accelerating through space. Solar sails are perfect for long, slow missions where you don't need to hurry, like exploring the outer solar system or even interstellar space. They're the silent, graceful dancers of the cosmos, gliding on the light of distant stars. But don't expect to win any drag races. Solar sails are all about patience and persistence. Their ability to harness the sun's energy means they can keep accelerating as long as they're exposed to light, making them ideal for missions that don't require rapid maneuvers. So what if you want to go even faster, even farther, and maybe even break the speed of light? Antimatter rockets are the final frontier of rocket science. They work by annihilating matter with antimatter, releasing energy on a scale that makes nuclear reactions look like a campfire. In theory, antimatter rockets could reach speeds close to the speed of light, making interstellar travel a real possibility. But there's a catch. Antimatter is incredibly rare, expensive, and dangerous to handle. We're talking about the most powerful and mysterious form of propulsion known to science, the kind of thing that could make Star Trek look like a documentary. But until we figure out how to make and store antimatter safely, it's mostly a dream. Their potential to unlock the stars is tantalizing, But the practical hurdles are immense. So what's the next step in the evolution of rocket ships? Thanks for sticking around to the end of this wild ride through rocket ship history. If you enjoyed this journey into the cosmos, drop a comment below and let me know which rocket type you'd want to ride into space. Don't forget to like the video and subscribe to CosmoBinge for more mind-bending space adventures. After all, the universe is out there. Let's go explore it one rocket at a time.